The speaker is Annalisa Massaccesi. She's a member here, but otherwise this semester, but otherwise you typically find her in the University of Padua.
Yeah.
And she changed the title. So actually the title she gave is Frobenius theorems for submanifolds and currents. But anyway.
Okay,
forgive you for changing title and please go ahead.
So, okay, good afternoon. I apologize for changing my title. And I thank you for your kind invitation from being here. So the topic I would like to share with you today is how we can relax Frobenius theorem and see how it works, if it works, for weak concepts of submanifolds. So, for instance, currents or tangency sets. Okay, so let me start with an introduction of these Frobenius-type problems, and then actually my seminar will be divided in two parts. One of them dealing with problems of contact sets, and the other one dealing with currents instead. Okay, so the introduction. We are given a distribution of vector fields, and thus we can always consider the generators of this distribution and pick a pair of vector fields, for instance, V1 and V2, at least C1, and consider this object, which is the Lie bracket. So we take the derivative of V1 with respect to the direction V2 and subtract the converse operation. I mean, take the derivative of V2 with along V1. We say as a definition that a smooth distribution of k-planes, which is spanned by this V1, Vk, again, for the rest of the seminar, I will be considering this Vi to be C1, at least C1 vector fields. We say that this smooth distribution is involutive at some point if this condition holds for every pair of Vi, Vj generating the distribution itself. We ask that the Lie bracket of each Vi, Vj computed at x0 belongs actually to the distribution of the distribution V, evaluated obviously at the same point x0. So what's our main nightmare, the main distribution violating this involutivity? We can think about the horizontal distribution in a Heisenberg group. For instance, we can consider the first Heisenberg group, just think about R3, endowed with these two vector fields, which are called horizontal vector fields, x and y, x being 1, 0, and then minus y over 2, and y being 0, 1, x over 2. Now, if you compute the Lie bracket of these two vector fields, the two-dimensional distribution, you see that at every point you're going to get 0, 0, 1. So the vertical line, the vertical direction, okay. And thus the distribution spanned by x and y, also called the horizontal distribution, is nowhere involutive because there is no way that this 0, 0, 1 belongs to the span of x and y for every pair of point x and y in R3. Okay, so, and this is the classical Frobenius theorem. Take a distribution of planes, as before, V of class at least C1, and what you get is these two implications that may seem like an if and only if, but it's not quite, so I tell you about them separately. So if we have a k-dimensional submanifold or surface tangent to a given k-dimensional distribution, meaning that at every point the tangent to this submanifold coincides with V of x, then V must be involutive at every point. And the second part of Frobenius theorem is telling us that actually if V is everywhere involutive, I mean in the whole Rn, then the whole ambient space Rn can be foliated, locally at least, with k-dimensional submanifolds, which are tangent to V. So you really have the nice foliation you wanted to have. What's the idea behind Frobenius theorem? You want to, you're given a pair of vector fields, and you want to build a surface which is tangent to this prescribed distribution of vector fields. Start from x0. And then what you can do is you move in the direction of x0. Now I'm using x and y as the two prescribed vector fields that I want to be tangent to. So you start from x0 and you follow x evaluated at x0 for a time t. And you reach some point x1. And then from here, you see what is y of x1, and you follow y of x1 again for the same amount of time t. And you end up here at x2. And then you do, I mean, it's a Lie bracket, but also called a commutator, you do the opposite thing. So you start from x0, you follow y evaluated at x0 for some time t, you end up at x3, and then you follow x evaluated at x2 for, again, same time t. Now, everything would be perfect, dreamlike, if the 2 points x2 and x4 coincides. But this is not what normally happens. Normally, the distance, the mismatch between these 2 points can be, you can really write down all the computation, but can be estimated in this way. So you have a t squared in here, and then since you're moving one time in this direction, the other time in this direction, and the other path, you get the Lie bracket between x and y evaluated at x0, and then some error terms, which are small. But then, okay, perhaps seeing this t to the power 2 here could be misleading, because you think, okay, but now I sent t to 0 and who cares? But if you want to build a surface out of this brick, this first brick of your construction, you have to make a lot of these errors. How many? Well, actually 1 over t to the power 2, which cancels with this. So you see, if you listen to this line of reasoning, you end up hoping that this Lie bracket is actually 0. But, well, you can rearrange things in such a way that the only thing which counts is that this Lie bracket does not exit your tangent plane. So this is the reason, the rough reason behind a theorem such as this. I mean, at least I hope I gave you the idea behind the second implication. Now, since I'm interested in weak submanifolds, obviously only the first part of the statement of Frobenius theorem is meaningful to me. So, being slightly sloppy, in the rest of the talk, I'll be referring to Frobenius theorem, just meaning this first implication. So I'll be saying the Frobenius theorem holds when the non-involutivity of the distribution implies that the tangency set is trivial, usually zero measure, zero area. And then from now on, for the sake of simplicity, I will assume that the ambient space has dimension 3, and my vector field, my weak submanifold, everything are of dimension 2. If there are things that have an advantage of this being codimension 1, I'll be honest, I'll tell you, okay? Otherwise, it's just for the sake of simplicity. And then one last remark, which I think is pretty important, is that we do have a toy model for this kind of problems that everyone knows very well. Is the calculus 2 theorems. Someone calls it the Poincaré lemma, stating that if you have a prescribed vector field, then there exists a potential for this vector field. So the vector field is conservative, actually, if and only if the ladder is curve-free. Okay, it's the same kind of relation, this being curve-free and being involutive, a differential relation that we need to be fulfilled.
One question. Triviality here means measure 0.
Something. I mean, it depends on the kind of statement we were after. So, for instance, in the first part of the seminar, it means, yes, measure 0. Okay, so let's start with the current free part of the seminar. So let's start wondering what we can do when we are given a non-involutive vector field and we want to maximize the tangency set, even if this distribution is generally non-involutive. So, okay, the tangency set of a prescribed non-involutive distribution is this set E, where the tangent to the set coincides with the distribution. Now, these two theorems are kind of classic. I mean, the theorem by Balloch and then the one by Deladio that I'm going to quote in a couple of minutes. So Zolt and Balloch proved in 2003 that if the S, so the tangency set, is S is not the tangency set. S is the surface which in which we look at the tangency set. So it's sort of our ambient, okay, our ambient surface. Yes. If S is C11, actually with C2 here, it's Frobenius theorem, then the area of the tangency set must be 0. So here we're considering really the area of the tangency set.
And non-involutive, of course, you mean that really at every point.
At every point, because otherwise, yes, because otherwise you have to start to localize things and make distinctions. So yes, I really mean Heisenberg, the horizontal distribution. Then there is an improvement of this result, which we can do, and it's pretty nice. We means Giovanni Alberti, myself, and Andrea Merlo. One can see that actually in Carnot-Carathéodory spaces, so spaces where you are given this kind of non-involutive distribution, all two rectifiable sets are trivial with respect to the distance given by this non-involutive distribution. This is more or less in the folklore for Carnot groups. And then if you talk with specialists in the field, they tell you, okay, but then you use Pansou differentiability theorem and you you get the same result for Carnot-Carathéodory spaces. We were pretty satisfied to find a proof which works without invoking Pansu differentiability. And well, this is the second kind of strong result that I want to show you. Now, suppose S, so the ambient surface is barely C1, not anymore almost C2, Balog was assuming. But imagine that E to have finite perimeter. Then again, you get the same Frobenius-like theorem, meaning that the measure of the tangency set E must be equal to 0. And from these two statements, you can start to guess where I'm aiming at. Because the truth is that there is a sort of trade you can interpolate between these two results. So if you want to allow S to be less regular, what you need is some regularity for the boundary of the tangency set. And this is going to be a leitmotif of this seminar. It's always a trade between regularity and regularity of the boundary. So this is the result we have. You can assume S to be C1 alpha with alpha bigger than 0, and E with a finite S perimeter, meaning that the characteristic function of E belongs to some fractional Sobolev space, with this S fulfilling this inequality. Then, again, Frobenius theorem holds the area of the tangency set must be trivial, 0. Okay, so how does this proof works? Obviously, I'll be sloppy and I apologize. So let's step back to the toy model. So think about prescribed gradient, prescribed vector fields. You want to find a potential. So you replace the notion of surface with a graph and call E prime the projection of the tangency set E on your domain, because now we want to build a function, not any more, say, a parametrization of the surface. So the question that we have is more or less the following. Imagine you are given a summable function, f, and you already know that it has a summable curl. Can you expect this implication that if f is equal to 0 almost everywhere in E prime, then also the curl of f is forced to be 0 almost everywhere in E prime? So this is what we...
What do you mean by the curl of f in this case? This is a scalar function, right? Or am I...
No. This is not a scalar function. Sorry, I should have called it...
So it's a vector?
Yeah, it's a vector field.
It's a vector field from R3 to R3? That's what you mean?
No, it's...
Because E prime is in R2, right?
Yes. Okay, yes. F is the gradient of the function I want to build. So the
F is the gradient of the function that you want to build on... okay, so we have to think about...
this to be the derivative
a two-dimensional vector
of the function. Yes.
And so the curl now, you just mean the dx1 of f2 minus dx2 of f1.
Exactly.
Okay.
The Gauss-Green.
Mm-hmm.
Okay, so this strong locality holds true if f is of class C0 alpha. You see the fact that these are the derivatives. You can read them. You can read it in here. The surface had to be C1 alpha, and here you're assuming f to be C0 alpha. E prime has a finite S perimeter, again with this condition on S, and the idea is more or less the following. So you start you want to prove that the curl of F is equal to 0, at least on the Lebesgue points of the curl of F. So you take the average of the curl of F on a small ball center at X with radius R. You use the Stokes theorem, and what you get is the flux of F through the sphere, the boundary of the same ball. And then, well, you can estimate this with the integral on the sphere of the norm of F. Okay, now I know I told you that F was summable, and now I am taking an infinity norm, but just to have an idea of how it would work. You end up having here the measure of the sphere with center at X with radius R minus the points where F is equal to 0. So you can take out immediately these points because you already know that F is equal to 0. And now what you want to say is that this average goes to 0 as R goes to 0. And this is a consequence of superdensity, which I'm going to introduce in the next slide. So now we thanks to this computation, we just want to know why this ratio is going to 0. And the reason is the following. First of all, let me introduce the concept of superdensity. So we are given a point X in, okay, now I call this set F, but it's obviously our E prime. And we say that a point is a superdensity point for F is you take the ball centered at X or radius R, you take out the set F itself, and actually you damaged your ball so much that the measure of what is left, the leftovers, is going to 0 even if you're divided by R to the power 3, and we are in R2. Okay. So this means being super dense, and super is because of this string, which is bigger here. Okay, and then there is this theorem by Silvano Della Dio, a consequence actually of Sobolev embeddings, saying that if a set has some fractional boundary, in the sense that I was telling you before, so the characteristic of F belongs to this fractional Sobolev space, then almost every point at F is a superdensity point. Okay, and this actually gives us what we want. Okay, now to complete the picture. From up to now, I've always told you results about the fact that Frobenius theorem holds, so very rigid results for tangency sets. But what we miss in the picture, and what is in this slide, is that actually these results are sharp. So if you drop the regularity of the ambient space or of the boundary of your tangency set, actually Frobenius theorem does not hold anymore. There is this classical theorem by Balog saying that there are examples of tangency sets of positive area, so non-trivial, if F is a surface of class C1 alpha, alpha less than 1, and V is a non-involutive distribution. Obviously, no further assumption on the tangency set is made. And okay, again, we have the interpolating result for fractional boundary. It's the same paper in, no, this is a different one, I think. A preparation with Giovanni and Andrea. So pick alpha between 0 and 1. This time, you see, alpha is less than 1 minus 2s. So it's the other inequality. Then for any distribution, there exists a C1 alpha surface such that the boundary of the tangency set has regularity S, so the characteristic function is in W(S1), and the tangency set has positive measure, so it's non-trivial. So comments on this result. If you take alpha to be equal to 0, this is Alberti's Lusin-type construction for gradients, paper dating back to 1991. Because, well, yes. And then, no, let me state it in here. There is obviously a strong analogy with Alberti's Lusin-type construction. The kind of construction is more or less the same, meaning that what you do to prove that there is this really nasty tangency sets, you start, imagine you want to start from a square. And then you allow yourself some room with some kind of frame, but you want tangency to hold at least inside these smaller squares, okay? So it's not a dyadic construction because you have these frames which are thick, but you start prescribing the gradient in this square inside. And then the role of the frame is to give you some room to attach the construction properly. Okay, you need rank 1 edges and everything. And then you start again subdividing your squares in smaller squares and smaller and smaller and smaller. And you can tune the thickness, the width of your frames in such a way that you have proper convergence. The point is that what I wanted to stress is that what you're doing with this kind of construction is exactly devastating the regularity of the boundary of your tangency set, because you're creating holes and holes and frames and frames. So it's pretty evident from this kind of construction that there is a relation between tangency to something which is non-involutive and the regularity of the boundary of the object. As a corollary, one obtains existence of non-trivial two rectifiable sets in R3 tangent to a non-involutive distribution. And mind that there is no contradiction with what I told you before, the unrectifiability of Carnot-Carathéodory spaces, because here we're talking about the Euclidean distance, while there we had the Carnot-Carathéodory metric. And then if you heard me speaking about this kind of results like last year, you may remember that I was talking about a gap between the Frobenius theorem, the rigid Frobenius result, and the existence of counterexamples, and that gap is not there anymore, thanks to some very helpful remarks by Thomas Schurponen. Okay, so this was more or less the situation for subsets of surfaces. What about currents? So just one very quick slide, and I apologize if I'm boring you, about the language of currents. So a current is a linear and continuous functional defined on the space of smooth, compactly supported k-dimensional forms. Its boundary is a k-1 dimensional current, so the dimension is the proper one, defined through this relation, which means I'm enforcing Stokes' theorem, because the action of the boundary of the current on a k-1 dimensional form coincides by definition with the action of the current itself on the differential of this first form, which has become a k-dimensional form. And then we have a mass, which is simply the operator norm of the current itself. Now, obviously, a generic current can be really messy and ugly, but a normal current starts being more reasonable. A normal current is a current with finite mass and a boundary with finite mass too. So, for instance, there is top dimensional normal currents are really VV functions. Okay. So the normal current, thanks to a sort of Riesz theorem, can be represented in this way. So you have an orientation, which you can call nu, and a measure, which is mu. And then also the boundary as an orientation, a k-1 dimensional orientation, which is nu prime, and an associated measure, which is mu prime. Where, okay, as I told you, mu and mu prime are positive measures, and nu is a k-dimensional vector field, mu prime is a k-1 dimensional vector. Now, an integral current is a normal current with a very nice representation. So it can be represented as the integral on a k-rectifiable set of this quantity, where this pairing is the orientation, the tangent to the rectifiable set sigma paired with the test function, the test form. And then we have a multiplicity. This is a number, an integer number, theta of x. Now, just, I know it's subtle, but just a remark. For the rest of my talk, I'm assuming T to be oriented by a unit simple two-vector field, because I'm, as I promised, I'm going to consider two-dimensional currents. So V1 wedge V2, but I'll be saying that T is tangent to some distribution if this unoriented condition holds. So the span of nu is contained in this distribution. So the difference between saying that T is oriented by something and T is tangent to something is that here you have a sign and below you have none. So you are allowed to flip sign. This is just a set inclusion. Okay, so and well, now I'm cheating a little bit, meaning that yes, we are considering two-dimensional currents in R3, so simplicity is something we have for free, while when the vector field is not simple, there are problems, there are additional problems. Okay, so now since one wants to understand how close integral currents are to proper regular submanifolds, one starts wondering if some classical geometrical properties of submanifolds still holds in the ambient of integral currents.
Annalisa, so here you didn't say it, but I assume when you're saying integral current, you want that representation for, or I mean, okay, so it's the rectifiability theorem, but you're okay. It's a normal current. Okay.
Yeah. Yeah.
So the boundary has finite mass.
Yeah. 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 Integral meaning that also the boundary has the nice representation. Yeah. Okay. So which are the nice geometric theorems that I want to test on integral currents? Well, of course, the first one is Frobenius theorem. And well, actually, Frobenius theorem works from integral currents, meaning that if T is an integral current with this orientation nu and a rectifiable set sigma as a support, and it's tangent to some C1 distribution, capital V, then V must be involutive at every significant point of sigma. And as a consequence, for instance, you immediately see that there is no integral current tangent to the horizontal distribution of the first Heisenberg. And then there is another property which is so stupid in the framework of submanifolds that nobody would waste their time to prove it. And it's the following: if you're given a submanifold, okay, there's some orientation, a submanifold with boundary, then the orientation of the boundary of the submanifold is a subset, is a subspace of the orientation of the manifold itself. Okay, this is really something very obvious, which is not in the case of currents. I mean, it's still true, but you must prove it. So if T is an integral current under, I'll be back on these assumptions later, but under very reasonable assumptions, you see that the orientation of the boundary, because this new prime is the orientation of the boundary, is a subset of the prescribed distribution at almost every point of the boundary. And as an assumption, you can ask one of these two things, which are, I mean, there is no hierarchy between the two of them. I mean, they're really independent. Either T is tangent to some C1 distribution V, or T is oriented by a vector field V, which is C0, which is barely continuous. But you see, T is oriented means that you keep the sign of the orientation, while T is tangent means that inside this capital V, you can flip. Okay, anyway, for integral currents, these two properties hold true. Now, what happens for normal currents? And for normal currents, you immediately see that these strong geometric properties like Frobenius theorem doesn't hold anymore. And you take, for instance, this example, which was given by Dvorsky in 1988. Take as a current you take the horizontal vector fields of the first Heisenberg distribution, so x and y really 1, 0, minus y over 2, and 0, 1, x over 2, the ones I showed you before. And then you take as a measure just the Lebesgue measure. Well, it turns out, just making a one-line computation, that this current is actually a locally normal current. But this distribution is genuinely non-involutive. I mean, anywhere. So we got a normal current with a non-involutive orientation. And if you look at the second property, I mean, the stupid property of the orientation of the boundary being a subspace of the orientation of the current itself, well, that is not true anymore. Because if you compute what is the boundary of this current T, it has a vertical component times the Lebesgue measure, and this obviously does not belong to the span of x and y. Okay, so now this theorem for normal currents becomes a definition. I mean, a normal current satisfies what we called the geometric property of the boundary at some point x0 if you have that the orientation of the boundary mu prime at x0 is a subspace of the orientation of the current itself.
Yeah, Annalisa,
Yeah.
but if I insist that I want actually boundary zero, is there any example? Or is
With boundary zero, I don't think so.
so for current of finite mass which has boundary zero, in
Which are
principle,
normal currents.
which are normal currents, but the boundary is exactly equal to zero, it might actually be that Frobenius theorem is still okay.
Yes, I think it could be. I think perhaps in the next theorem we will have the proper
answer?
Yeah. Okay, because yeah, if not in the following theorem, we can look for the answer in the proof of the theorem. So take your measure mu prime, which is the measure associated with the boundary. Split it in a part which is absolutely continuous with respect to mu. Mu is the measure associated with the original current, and the singular part. Okay, so I mean, Giovanni Alberti, myself, and Evgeny Stepanov have the following theorem. A normal current tangent to a C1 distribution satisfies the geometric property of the boundary mu prime S almost everywhere, and mu prime A almost every x at which V is involutive. So obviously there is no contradiction with Dvorsky's counterexample, because you see here mu prime, is all in mu prime A. It's all absolutely continuous with respect to mu, and there is no involutivity at any point.
But then I'm not sure this goes into the direction I'm saying, right? Because if the boundary of t is equal to zero, then your theorem, of course, is true kind of trivially, because they're both zero measures.
Exactly, but this is a theorem about the geometric property of the boundary. And you wanted something about
something about the involutivity. Yeah. Okay, so but you think the method of the proof actually?
Yeah.
Okay.
Well, just to complete this overview, the other question that one may wonder is about the sharpness of Dvorsky's counterexample. I mean, obviously, if you want to produce such a counterexample, you pick a pair of non-involutive vector fields, but you have some freedom in choosing this measure here. So you wonder if your only choice is the Lebesgue measure, or you can do something different. And actually, the answer is not. You have to take the Lebesgue measure. Why? Because there is this result, meaning that if you have a two-dimensional normal current, which is tangent to, ignore that, I always forget to erase this, Hormandes distribution, non-involutive distribution V, then mu must be absolutely continuous with respect to L3. So this thing of involutivity, non-involutivity is really polarized, meaning that where there is involutivity of your prescribed distribution, it's involutive, so you have the classical Frobenius stream, you have nice surfaces which are tangent to your distribution. So nice surfaces, and of course also integral currents, if you want to think to submanifolds like integral currents. So genuinely two-dimensional objects. While in the parts where your distribution is non-involutive, your current must be as spreaded as we can have. I mean, this is a two-dimensional current, but the measure associated to it is absolutely continuous with the three-dimensional Lebesgue measure. So this non-involutivity produced a spread of your current. And of course, it ruined your boundary. And yes, this means that any current, in our example, this means that Dvorsky's counterexample is actually optimal. Okay, so just to conclude, some open questions. First of all, what about Morgan's decomposition problem? This is another problem, and perhaps I can write something in here. For reasons connected with the second question, which is the Lavrentiev phenomenon in the Plateau problem, you wonder if you can foliate a normal current with integral currents, because because you want to exclude a Lavrentiev phenomenon in the Plateau problem. So if you have a normal current T, a Morgan's decomposition is a decomposition of your current as an integral of integral currents, R lambda in lambda. Okay? In such a way that the mass is decomposed accordingly. So, I mean, with respect to the very same lambda, you get the decomposition of the masses. And actually, if you want a proper Morgan decomposition, here you have to ask that also the masses of the boundaries are decomposed accordingly. This is the Morgan decomposition of a normal current in integral currents. Okay, and would help a lot to have such a decomposition, as I was saying, for the Lavrentiev phenomenon in the Plateau problem. Well, thanks to the theorem I told you, thanks to the validity of Frobenius theorem for integral current, we can already say that a Morgan decomposition cannot exist. I mean, not always exist, because in particular, this condition forces the orientation of your integral currents to be the same as the orientation of T. But if you pick a non-involutive orientation, T is allowed to have it, while an integral current cannot. Okay, so perhaps relaxing this condition or speaking about a decomposition in rectifiable currents without asking the finiteness of the mass of the boundary would have, I don't know, it's open problems.
Wait a second, your example is in codimension 1, right?
Yeah.
But in codimension 1, you have a Morgan decomposition. Can't I take the Goaria formula on BV?
Yes, of course. Wait. What's the point in codimension 1? You have its Goaria formula. Yes, I agree. It's Harpit's decomposition.
Right.
What's the point in that?
I mean, okay, so I can do it for, I mean, it's not that it's normal, it's really without boundary, because I can do it for the derivative of the function. So in particular, that proves the answer to my question, right? I mean, certainly you cannot get a counterexample. Certainly you cannot get a counterexample to Frobenius in, say, codimension 1.
Yes.
You have to go to codimension 2. Because you will use the area formula the coarea formula to just prove.
Yeah,
to prove it. But I need that the boundary is equal to 0.
Yeah.
I mean, I will like. It's unclear that I'm actually able to have a decomposition like that if the boundary is not equal to 0, right? So because you're using the BB function to just say that your current is the derivative of the BB function, but to say that your current is the derivative of BB function, you really need the current to be closed.
Yeah.
right? I mean,
Yeah,
if you have a boundary that does not hold. Okay.
Yeah, perhaps also, I mean, dropping this one.
Right.
have a lot
Right. I mean, of course, if my mass of the boundary is equal to 0, then I don't have to care about the second condition, right? So then I can use the quadratic formula. But yeah, I see where's the problem.
And then another question that I mean, I'm really fascinated about it is that if we can quantitatively relate non-involutivity and non-integrability, meaning that, of course, there is a lot of space, a lot of shades between being a measure concentrated on a k-rectifiable set and being the Lebesgue measure in Rn. And perhaps you can measure the spread of your current just measuring the non-involutivity of your distribution. Or if you want, in Carnot-Carathéodory's terms, looking at the strata of your distribution. And yes, my last question is, does it help with the problem of calibrated geometries? Because here we have ways to prescribe a tangent vector field, or to say, okay, that cannot happen. So this is, yes, another question that I've been very interested to. Yeah, just I don't have time anymore, but quickly, the idea of the proof of this theorem. So Frobenius theorem holds for integral currents, because I think it might be helpful for someone. Yes, just let me say that the Hodge star operator of a vector field is the way to put in a Poincaré duality a vector field with a form. And in particular, if you take the Hodge operator of a k-dimensional vector field, you get an n minus k form. So for instance, in R3, if you start from a two-dimensional vector field, what you get is a one-dimensional form. What is the divergence of a two-dimensional vector field? Well, you can take it as a definition. Up to a sign is the Hodge of the exterior derivative of the differential or the Hodge of the vector field. I mean, you start from a two-dimensional vector field. You make its Hodge and you get a one-dimensional form. You take the differential, so it's a two-dimensional form. You take the Hodge and it's a one-dimensional vector field. So as it happens, as it always happens with the divergence, you lose one dimension. Well, this is the proper formula. Okay, and now and by Cartan's formula, what you see is that if you take a two-dimensional vector field and you consider its divergence, it's something along V1, something along V2, and then the Lie bracket of the pair. And this is very interesting because then you can build this very helpful form, one-dimensional form. So you take your pair of non-involutive vector fields, V1 and V2, and you just take their Hodge star associated one-dimensional form, which is alpha. Well, you can do the computation, and what you see is that if you take this V is V1 wedge V2, and you take the restriction of this V to alpha, it's 0. But if you take V restricted to the differential of alpha, is not 0 precisely because of the non-involutivity of the vector. Because here at a certain point, you have the exterior product of V with the divergence of V, and the divergence of V involved the Lie bracket. Okay, and then take this current. T itself, the one oriented by V, restricted to alpha, okay? This current is 0 because of the first property. But, and thus its boundary is 0. But then you make the computation and what you get is that the boundary has this form. So this summand is equal up to a sign to this summand, which you can summarize in this formula. So remember, nu was the orientation of the current, nu prime was the orientation of the boundary, mu was the measure associated with the current, mu prime was the measure associated with the boundary. And well, from this relation, you can read pretty much all the theorem I've listed about currents and Frobenius. For instance, take an integral current. Then you know that mu is singular with respect to mu prime. So when you have 0 on this side of the identity, and you know that mu cannot be 0, you must have that the exterior product of nu and the divergence of nu must be 0. And this is precisely the involutivity that we wanted to prove.
So if the current is normal, mu prime is equal to 0. That's what you were saying. If the current is normal, there's no boundary. So mu prime is equal to 0, right?
If the current is normal, why there is no boundary if the current is normal?
Sorry, if the current has, so if you replace the normality of the current with having like cycle, then the boundary is equal to 0.
Yes.
Mu prime is equal to 0.
Exactly.
And so this will prove you that
then you must you must be involutive where mu is not 0.
Where mu is not 0. Okay. And this is not depending on the fact that you are in dimension 2 and 3. So this you can do it in general.
No. This you can write it in every dimension.
In the appropriate algebra, you can do it with the appropriate algebraic preparations.
Yeah. Well, the problem, the algebraic preparation is really related to the fact that the Hodge star operator works badly with the dimension and codimension. Yes, okay, and this is really everything I wanted to tell you. So I really thank you for your attention.